All right, so hello friends. This next step in our adventures through graph theory, we're going to be looking at something called minimal spanning trees. Now, reminder about what we've been doing before. First off, we started with Euler networks. And an Euler network being an Euler path or an Euler circuit, we wanted to complete a path or a circuit around a graph crossing each edge exactly once. And I remember that Euler gives me the edges. I wanted to cross every single edge exactly once. And we had Euler's theorem to decide or to determine or to show us whether or not our graph contained an Euler path, if there were exactly two odd vertices, an Euler circuit if there were all even vertices, or if neither an Euler path or circuit was possible, if there were more than two odd vertices. After that, we explored the traveling salesman problem in light of Hamilton networks. Now, Hamilton network, we were all about crossing each vertex exactly once. And then if we had a path, we can begin and end at different points, just so long as we hit every single vertex. Or we had a circuit in which we crossed every single vertex and returned back to the start. In that sense, we had a loop, and each vertex had two edges attached for our subgraph when one edge entered the vertex and one edge left. Today, what happens if we don't need a circuit? What if we just need to branch out and reach everything? So with a computer network, for example, if we've got our main central hub, say this one in the bottom left corner, and we need to branch out and hit every single computer to connect everything, well, we could connect the two computers on the left. I can connect the computers along the top. I can connect the computers horizontally. And then I can link together the computers vertically as seen right there. Now in that sense, every computer has been reached. Every computer has access to our central terminal. Different from Euler, Euler crosses every single edge. Well, we're going to be trying to do this. We're trying to reach every single computer using the least possible cost. Now, I have a weighted graph here where the numbers along the edges represents the weights or the costs. We don't need a circuit here because if we do connect things, well, we've got some redundancy and I'm paying for that extra line. I just need to branch out and connect everything. There's a way to go from every single computer, in a sense, back to the start. No matter where we are, we have a way of connecting every single computer. And in that sense, everything is located on the network. But looking at this, you can see maybe that's not the most efficient way, especially if each of those values represents a cost. We might want to do with fewer of those 18 unit edges. So that's what we're going to be looking at today. Few definitions that we take ahead of time. A subgraph is going to be any collection of vertices and edges that themselves represent a graph. So we actually did this with our Hamilton paths or Hamilton circuits, where we created a subgraph or identified a subgraph. It's a smaller collection of our graph. Now, we're specifically looking at a tree. A tree is going to be a subgraph that is connected, meaning every single edge, any existing edge in a subgraph is connected to every other edge. Like there's no branches hanging off by themselves and contains no circuits. So in that sense, there's nothing that loops back into itself. A tree branches off, it reaches, it connects with the vertices. So it links one vertex to another vertex. Now we're going to be also looking at a spanning tree. A spanning tree is a special type of tree. So first, we fit the tree definition in that we are connected and there are no circuits. It also contains all vertices. So we must reach all points, all nodes, all vertex points on our graph. So that's what I mean by spanning. It reaches everything. We've got 4 examples here, and our 4 subgraphs. You can see the blue highlights. We're going to be looking at graph 1, 2, 3, and 4, identifying are the elements connected? Are there no circuits contained? And if there is there a circuit, then it's not going to be a tree. And do we include all the vertices? If these are true, that gives us a tree. If all 3 are true, that gives us a spanning tree. So let's take a look at subgraph number 1. If we look at all of those points there, between any line there, everything's connected. We can contain everything inside one circle. So that's going to be connected. Are there any circuits in subgraph 1? Well, if we start at any location, can we loop back into itself? No. So there are no circuits. That's also true. So right now, we have a tree. Last part, do we contain every single vertex? Well, in subgraph 1, we are missing vertex F. So that's going to be false. Therefore, it is not going to be a spanning tree. Now let's take a look at subgraph number 2. If we like this, now are all the branches connected in subgraph 2? We've got this section from C to G to D to B, and then E to A to F. Those are separated. In a way, I can draw a line that splits that into 2 different parts. So that's an example of where our subgraph is not connected. So I'm going to say F for false. I don't even care that there are no circuits. That is not going to be a tree because there are 2 different parts. That's what it means to be not connected. Let's move on to subgraph number 3. So we've got C to G to D to B. We've got that over to E. We've got over to A. We've got F, and we've got G. Is it connected? Yes. Every piece is connected in there. Are there any circuits? Well, if we look at this D, E, F, G, back to D, it's closed off. So there is like this inside section and an outside section. There's a part that, no matter how we draw that, there's an inside. That's a circuit. So because there is a circuit there, I'm going to put F for no circuits. That means we are not a tree. A tree, thinking like out in nature, does not grow back into itself. And lastly, let's take an example of subgraph 4. We've got all of those pieces, all right? It's connected, different from subgraph 2. I cannot split it into multiple parts. So we are connected. We do have no circuit, or we don't have any circuits. Now the next step is we include every single vertex. So first off, we are a tree, but because we also have that every single vertex in there, we are also a spanning tree for that example. Now, how are we going to use this? We start off in class using something we're trying to find the minimum total distance. This is going to be very similar to our nearest neighbor or greedy algorithms for the traveling salesman problem and Hamilton circuits. We're going to be looking at what's called a minimal spanning tree. So when we have a weighted graph, and weighted, we have costs associated with that, with crossing each edge. We want to have the sum of the weighted edges is as small as possible. Now we're going to be using something called Prim's algorithm, which is kind of what makes sense. So our first step, and if we want to have the smallest possible spanning tree, first off, everything needs to be connected, there have to be no circuits, and we have to include every single vertex. But we want to do so with the smallest possible sum. We're going to start off by selecting the smallest edge. So I'm going to highlight that edge C to F there. So we're going to select the smallest available edge. After that, let's look around. We still want to make the smallest possible total sum. So I'm going to look for the next smallest number. We've got that one. My next is BD, which is a sum or a distance of 2. We're going to repeat. After the 2, we see there's a 3, so I'm going to use that 3. Now we're still not connected, even though some of the edges are beginning to join together. But after the 2, we've got the 3. After the 3, we can see I'm going to repeat and select the smallest available edge. The 5, ooh, that's a problem. The 5 is not allowed, so I'm going to undo that. The 5 is out because it creates a circuit. So when I say repeat and select the smallest available edges, we want to make no circuits. So I'm going to say making sure not to create a circuit. We can't use that 5. After that, we're going to use one of the 6s. Up next, from E to F, we also have 6, but that's not usable because that would also create a circuit. And after that, well, we look around and we see A is there. We just need to close off and connect A. So now we can see I've got a graph where every vertex is connected. There are no circuits. And we did so by selecting the smallest available edges. So I'm going to put in step 3 here, where we're going to continue until we've reached every single vertex. Let's try one more. We've got this item where we're going to find the minimum spanning tree. So we look anywhere on the graph, and we can see that 7.5 is our smallest available edge. After the 7.5, the 12.0 is our next smallest available edge. After the 12.0, the 12.4 is the next smallest available edge. And then we have 15.3 is our smallest available edge. And at that point, we have a complete spanning tree. And we did so by selecting the smallest available edges. That's what we've got. Minimal spanning trees. Catch you next time.